Morning, everyone. Welcome to our Hub webinar on the optimization of fabric architectures provided by the EPSRC Future Composites Manufacturing Research Hub. My name is Alex Hammond, and I'm the Hub Deputies Manager. Before we start the presentations, please note the following. A recording of the webinar will be put on our website, and questions can be submitted via the questions facility on your screens. Participants should put the name of the speaker their question is directed to at the start of their submitted questions. I will read out selected questions once all presentations have finished. You'll see the agenda on your screen. Our Hub Director, Professor Nick Warrior from the University of Nottingham, will now give a brief introduction to the Composites Hub and workstream.
Well, thanks, Alex, for that. So yes, welcome everyone, and thank you for joining us today. This is our third Hub webinar. I'm going to give you a very brief introduction to the Hub and to talk a little bit about what we're going to expect from this webinar today. So the Hub is a substantial national investment, and the aim is to expand the national research effort in polymer matrix composites. So it started in 2017 and it will finish at the end of 2023. There are four key drivers. The first is research. We want to optimize the composites manufacturing and science technology research in the UK. We want to create a pipeline of the next generation technologies and feed this through to the HVM catapult network and then into industry. We want to train the next generation of composites engineers, and we're looking at about 150 people. And we want to grow the UK community and the international communities. So here are our UK academic partners. You'll see that we've got 15 UK universities working in the Hub, and this covers most of the composites manufacturing research activity in the UK. There are still some universities that we want to continue to engage with. And you'll see we have a substantial industrial partner base, and we're very grateful to those industrial partners and proud to have them. So you'll see that we've got all of the sectors, the really substantial sectors in composites manufacturing, from defense, aerospace, automotive, and the partners include all elements of the supply chain. So this is a very quick overview of the structure. So we have two grand challenges, and these are industry-inspired grand challenges, and these are fed by 5 research themes. So in all, we have 29 projects in these research themes, 6 core projects, 9 6-month feasibility studies, and 4 fellowships, 28 PhDs, 39 NGDs, and 22 postdocs. Now, the most effective way we have found to engage all of these projects to meet these research themes is to go for a work stream approach. And you'll see that we have 8 work streams. Now, today's webinar is all focused on work stream 2. And this is we try and categorize our work streams by these daisy diagrams here. So you'll see at the center of the daisy diagram is our core project, Optimize, and Andy and Prasad, Louise, George, Vivek, and Roy will all talk about this later on. Mikhail too, I nearly missed out Mikhail. And you'll see that project collaborates with 3 other core projects in dark blue. There's 1 feasibility study in light blue that has supported this. And you'll see the industrial partners who are all feeding in to this project. You'll see that the institutions, the universities, also feed in with support for PhDs and NGDs. So the presenters today, so the first man up is Andy Long, who's leading the Workstream 2 core project, and Prasad will talk about his work looking at manufacturing technology to support that. Louise and Mikhail will talk a bit about the TexGen work at Nottingham. George will talk about his PhD looking at manufacturing 3D woven T-joints. And then Vivek and Roy will talk about the manufacturing work, the creative design work that's been going on in Manchester. And I'm looking forward to these very much indeed. So, without any delay, welcome, thanks, and thanks for presenting today, Andy.
Thank you, Nick. So yes, so as Nick said, up next is Andy Long, followed by Prasad. So up to you, Andy.
Great, thank you very much. Thanks, Nick, and thanks, Alex. So I'm going to give a bit of an introduction to the project, and then my colleagues are going to give you a lot more detail. But the project we're talking about is called New Manufacturing Techniques for Optimized Fiber Architectures, and it's really about how do we make particularly 3D preforms for composite materials. How do we improve their performance? How do we optimize their performance? And also, what manufacturing techniques can we develop to make new material forms that give us the properties that we really want? So this is about 3D preforms, so things like 3D woven materials or 3D braided materials. And we know that those materials offer better, in particular through thickness, mechanical properties than you would get from, say, laminated composites. We also know that they can be manufactured to a near net shape. In particular, you can put bifurcations into 3D weaves that allow you to open them out to make things like T-pieces. We know that some of these materials are already being used in industry. 3D angle interlock composites, for example, are being used in the aerospace industry as we speak. But we know that the selection of the right architecture, the right design of the preform is a challenge because you've got an awful lot of variables that you can play with. So how do you determine the right material form, and also how do you manufacture the right architecture? Those are both key challenges. So the key questions we're looking at then is how do you design a reinforcement which is most appropriate for a particular application, considering both the mechanical performance that you want, but also manufacturing consideration, including how easy it is to infuse successfully through a process like resin transfer molding, for example. And then can you manufacture that optimal reinforcement with conventional equipment, things like jacquard looms that are available to produce materials commercially now, or do we need new technologies to give us the material forms that we really want? So in this project then we're taking an optimization approach, and we're really doing this in two ways. First of all, with manufacturing constraints, in other words, looking at material forms that you can make with commercially available machinery and where there are commercial suppliers now, how can we optimize the material form for a particular application by varying the pattern, the weave pattern within a 3D woven material, perhaps the type of fiber, the spacing and weight of the yarn, for example. So that's kind of approach one. But approach two is really to ask the question, what if we relax the manufacturing constraints? In other words, what if we model materials that you can't make with commercially available material manufacturing solutions? What then do you end up with as an optimized material form for a particular application? And then we can consider the development of new manufacturing technologies to realize those new optimum material forms. So really the way that this works is we're optimizing the material form using computational techniques, which I'll come on to briefly, and then our colleagues at Manchester are developing new manufacturing technologies. And the sorts of things you can see on the slide represent the kind of areas where we're developing new manufacturing processes. Prasad will talk a lot more about this, but we're looking at things like multi-axial woven materials, where you don't just have 0-90 yarns, but you have yarns at any angle that you like in the plane. That's one of the technologies being developed. And another is cylindrical materials with through thickness reinforcements derived from a combination of a braiding and winding process. So final slide from me before handing over to colleagues to give the details. This kind of works in partnership between Nottingham and Manchester. So the team at Nottingham are working on the optimization and the modeling side of this. The team at Manchester are working on manufacturing. So for modeling, we generate models using our TextGen software for the material form that we're interested in. We predict the material properties of that model. So for example, the mechanical properties of a composite with that reinforcement inside it, but also the permeability, infusibility, if you like, of the material as well. And we can do all of those things automatically, and we put those into an optimization framework that lets us determine the optimum material form. And then colleagues at Manchester are developing manufacturing techniques to help us to realize some of these optimum forms. And they're looking at two options there, techniques derived from weaving and techniques derived from braiding or winding. And Prasad will say more about those in the next presentation. And then finally, we're applying all of that to some demonstrator components. And those are a vehicle floor pan, which has been supplied to us by the AMRC, and also a pressure vessel that's been supplied to us by Luxfer. And with that, I'm going to stop and hand over to Prasad.
Thank you, Andy. So Prasad, if you'd like to join the stage.
Yeah, thank you, Andy, for introducing the topic. I'm going to talk about how we try to realize this dream of unconstrained manufacturing. Andy set a problem at the very beginning. We can optimize, but sometimes we can't manufacture on conventional jacquard and various machines. How do we move forward? So we decided at the very onset that we move away from conventional machines and actually do a bottoms-up approach. You have this architecture, and how do we deliver through manufacturing? So we use robotics and flexible automation to do that. So we work with Nottingham and also with other partners in the hub and our industrial collaborators on various aspects of the project. So essentially, we take a building block approach. We take modular robotics and create a loom or create a winding machine, create a braiding machine to deliver exactly what we want. And in doing so, we have come up with various architectures. For example, there's a multi-axial woven architecture, a cylindrical 3D preform, or an ultra-thick multi-axial preform, essentially to push the boundaries of manufacturing. For example, if you're familiar with the weaving technology, conventional jacquard weaving looms have been programmed and adopted with appropriate creels and tensioning systems to create what we call 3D weaves, by which we mean creating multi-layer fabrics with various binder architectures. And also by creating slits and pockets, you can create what we call origami-like structures, T-sections, pi-sections, and various reinforcements that some of you are familiar with. So with this technology, as you can see, typically this was designed for making a broad woven cloth, typically out of cotton fibers, for example, in the textile industry. We adopted and modified to weave carbon fibers, but not quite to have the ability to do true three-dimensional structures. For example, in a woven fabric made of a jacquard machine, we are restricted to knot 90 configuration along with Z binder fibers, and limited three-dimensional capability, limited thickness, and mainly certain origami-like shapes. So the first step is to how do we overcome this limitation? And in braiding, or what we call cylindrical type of structures, we looked at two types of structures. One is like a planar or that kind of structure. Second is closed surface structures like tubular kind of structures. Both find applications in composites extensively. If you look at braiding, whether it is a conventional maple braiding or radial braiding, you create essentially two-dimensional single-layer cloth in a tubular form. So if you want to make a composite, say, propeller shaft or something like that of a decent thickness, you need to braid back and forth to create a sufficient thickness. So that would mean these are two-dimensional layers, so interlaminar properties would have some problems. So what we try to do within this program is to work on two different manufacturing platforms. One is 3D weaving type of structures. Second is 3D braiding-like structures. So the objective is to create truly three-dimensional integrated structures with multi-axial capability. That means you can put 0, plus, minus theta, 90, any orientation you like. So that suddenly removes the manufacturing constraint significantly. And try to make near net shapes with variable tau densities. So you can actually, almost like 3D printing, you can define, I want fiber orientation and density of fibers in this region, or I want thickness this region. We should be able to develop a machine and program it accordingly. Similarly with 3D braiding as well. Looking at the journey of 3D weaving, we started working in 90s at Manchester, used an old Lancashire loom with a Jacquard engine at the top to create three-dimensional architectures. And we learned from this, and around 2012-14, we set up a Dornier with a Stobly Jacquard loom and started modifying the machine to increasingly create what we want to create. But within 2-3 years, we reached the limitations. We were able to produce quite interesting structures, but we cannot go beyond a certain point. That's when we started actually conceptualizing and developing a robotic 3D weaving process. And that's what this slide shows, the multi-insertion three-dimensional weaving. And this technology has been patented both in Europe and US. This gives a combination of multi-insertion weaving. So that means instead of building layer by layer, we can put up to 22 weft yarns simultaneously into the fabric, and we can also sculpture it. We can change the thickness, width, and so on and so forth. Just to give an example of a kind of a structure you can make is for example, a T-section coming out of the loom as a kind of a protruded kind of a beam. You're not actually making an origami and opening it up. In doing so, actually, we cleverly incorporated off-axis fibers. For example, the so-called angle interlock bind yarns becomes the plus-minus yarn in the vertical section, and that's where we want. So we can create multi-axial configuration, and also the important thing is the noodle section, so-called noodle section that we normally have in origami structures does not exist here. It's a uniformly thick structure with everything fully integrated. What it means is this structure not only improves the fiber architecture, it will also improve the off-axis loading. That's one of the major problems with conventional 2D composites, where when you try to apply off-axis load, you experience delamination and all sorts of things. But here, being truly integrated, almost like a billet-like shape, you can postpone significantly the delamination problems. There's an example shown where we have been weaving a T-section coming out of the loom. And we also worked on the platform where we create near net shapes using what we call robotic fiber placement, stitching and tufting technology. I'll come back to it in a moment. And then we have been working on another platform, what we call quasi 3D winding, working with a company called Signet TexGen. They launched this 3D winder based on the concept that we work together. And what this creates is not 2D layers, not through 3D, but it's what we call quasi 3D, where individual taus have quite a complex geometry. And there is some kind of, not interlacement, embedding between different layers. So you get better damage tolerance in this process. And then we developed what we call quadraxial braiding, where we put triaxial braiding with a hoop winding, again to open up the limitations of the braiding process. And then using that as a basis, we started developing what we call a 3D braiding technology, where we could combine the concept of helical winding and through thickness interlacement. This is a small desktop machine, and this is being scaled up to a much larger version to create what we call cylindrical preforms. It doesn't have to be perfect cylinder. It can be box section, any closed section with variable shapes, with multiple layers with through thickness binders. That's what we're trying to achieve here. Just quickly to highlight, we have 4 PhD students working alongside, especially to exploit the technologies that are developing between Nottingham and Manchester. And Sarvesh Dhiman has just finished his PhD. He looked at the effect of binder configuration on the residual stresses developed during the composite manufacturing process. Ginseng Park actually developed quite a complicated machine for fiber hybridization and micro wrapping, commingling, stretching, all sorts of clever techniques we can do to mix dissimilar materials and create three-dimensional composites. Kazi Saurabh has worked along with three-dimensional weaving and essentially studying how the binder architecture and binder tensions affect both the permeability and stress distribution within the composite, how the damage starts and evolves. Syed Abbas is almost in the middle of his PhD, is using robotic preforming driven by computer vision and deep learning. He developed these algorithms to actually learn the fabric architecture and start identifying individual unit cells and assign parameter geometries. And essentially, you can continuously monitor during the manufacturing process and optimize and remove any possible defects. So that's the primary goal of our manufacturing platform. And my colleagues, Vivek Konchuri and Shankar Roy, towards the end of this webinar, will actually demonstrate 2 case studies demonstrating how these technologies are used in that product demonstrators. Thank you.
Thank you, Prasad. Very interesting presentation. So the next presentation is on numerical framework for optimization of fiber preforms, and that's presented by Dr. Michael McNeeve. You're on mute, Michael.
Thank you.
Yeah.
Hello, everyone. My name is Mikhail Matveev. I will be talking about a numerical framework we developed for optimization of fiber preforms. This will cover part of the project Andy talked about at the very beginning. So as it was mentioned before, 3D reinforcements offer better mechanical properties in the through thickness direction and also can be manufactured to the near net shape. Angle interlock 3D fabrics are already used in the aerospace industry, in particular the fan blades in the LEAP engine manufactured by General Electrics. But again, the industry uses only several conventional architectures like angle interlock or orthogonal weaves. And in all of these architectures, warp and weft yarns are always orthogonal to each other. So there is a lot of room for optimizing the fiber architecture. You can optimize the weave pattern, you can optimize the toe size, but also you can create 3D architectures where warp and weft yarns are not necessarily perpendicular to each other. So there is a need for some sort of optimization tools to arrive to better architectures than it's possible now. So hence there are several research challenges: how to optimize internal structure of 3D composites, and then how to manufacture these reinforcements. The latter has been slightly covered by Prasad Patluri in his previous presentation, and I will talk about the optimization of the internal structure of 3D composites. To optimize the architecture of 3D composites, we developed a framework, a numerical framework, which consists of several steps. The first of them is creating model of a reinforcement using TexGen software. Then once we got the model of the reinforcement, we then move to the Meso-scale simulations, where we can extract material properties of the reinforcement, be it mechanical properties like tensile stiffness and strength, or processing properties like permeability. But in this presentation, I will be only talking about mechanical properties. So once we've extracted material properties from the Meso-scale geometry, we can move on to the micro-scale, where we simulate structural performance of an entire part as if it was manufactured from the reinforcement we are interested in. And when we evaluated the performance of the structural composite part, we then can pass it onto the optimization algorithm. In our case, we use genetic algorithm, which will then evolve the solution in sort of like a loop fashion, and will arrive to an optimum. So the main challenge is how to link the meso-scale properties with the macro-scale properties, and also how to perform a multi-objective optimization, so to improve several properties simultaneously, or improve mechanical properties and processing properties simultaneously. So the first step in this framework is related to TexGen software, which is an open source software developed by the Composites Research Group at University of Nottingham. It's freely available at this website, texgen.sourceforge.net. And TexGen is a preprocessor used to model geometry of textile structures. To be specific, TexGen sits right in between the microscale modeling and macroscale modeling. At the meso-scale, where TexGen is used, we look at the internal structure of textiles. We look at individual toes and how they interlace with each other, but we do not look at individual filaments. Using TexGen and its graphical user interface, it's possible to create different 2D textiles, 3D textiles, including orthogonal, angle interlock, and layer-to-layer. And then it's possible to create input files, which then can be used for finite element solvers or for CFD solvers to predict material properties. What is important here is that it's possible to program TexGen to create these models in automatic fashion. So we can parameterize our model by several parameters and generate it on in a batch mode, just driving it from an external program. And it's very important for any optimization framework, an ability to generate the models quick and without any kind of like user interaction. As I said, TexGen software is freely available from this website. You also can find the source code on the GitHub, along with the sample codes for scripting TexGen, and also tutorials on how to script TexGen. Since 2006, when the TexGen was released to the open source, there has been almost 50,000 downloads from all over the world. Now I'll talk a bit about multi-scale modeling, and primarily I will talk about how we can get from the meso-scale to the macro scale. So 3D woven composites and 3D composites in general are only 1 unit cell in thickness. So which means they are relatively thin compared to their in-plane size, where the unit cell is repeated multiple times in X and Y directions. So how to get macro scale properties from this unit cell? And actually, what properties do we actually need? If we extract only tensile stiffness, then actually we will see that the binder path has very little influence on the tensile stiffness or shear stiffness for that matter. But what about flexural stiffness? And flexural stiffness becomes important when we think how to model the composite at the macro scale. The most efficient way to model composites at the macro scale is using shell elements, because usually composite structures are relatively thin but have large in-plane dimensions. So we actually do need these flexural properties to model, for example, simple 3-point bending. But how to get the right properties for this model? To get the right properties, we need to apply specific boundary conditions to our unit cell. Three problems consist, 3 boundary conditions represent 3 in-plane deformation modes. One is the stretch in X direction, stretch in Y direction, and in-plane shear. And 3 other deformation modes are out-of-plane deformations, bending around X-axis, Y-axis, and a twist. And simulating these 6 loading cases will give us a generalized stiffness matrix which fully describes the composite material as a plate. In classical laminate theory, this stiffness matrix is often called an ABD matrix, and I'm sure that many of you are familiar with it. This work has been done in collaboration with Professor Shiguan Li from the University of Nottingham. Also, when we extract material properties using these boundary conditions, we will be able to get a bit of an insight on how much the binder path actually, how much influence the binder path has on the flexural stiffness. And we will see that just by changing the binder path without changing its weight, its toe weight, or something like that, we can increase flexural properties by 10%. Something we will not be able to see if we use only the first 3 deformation modes. So now I'll talk a bit about the optimization routine we use in this project. So when we talk about optimization, we have a particular problem in mind. And here we start with a design of a reinforcement and a part geometry. Here it is an automotive floor panel for which we want to maximize the bending stiffness with no increase of weight. In the optimization framework, we start with a parameterized model of the unit cell where we parameterize toe sizes, number of layers, binder path, and orientation of each individual layer. We can homogenize this Meso-scale geometry and obtain stiffness matrix, an ABD matrix, which we then pass on to the macro-scale simulations, where we perform a finite element analysis on the structure we want to optimize. So in this case, we apply bending load to this structure and obtain its stiffness, which together with weight form objective functions for the optimization. These objective functions used in the genetic algorithm to compare the designs of the reinforcement with each other. Then good designs will be mutated or tweaked slightly to get a possible improvement, and also good results or good designs will be crossed over. So good features will be taken from some designs, merged with good features of other designs, and again, the algorithm will see if it leads to an improvement or not. An important point here is that we do not limit ourselves to conventional architectures here. We do not optimize only, say, orthogonal weaves or angle interlock weaves. We relax the manufacturing constraints and we consider off-axis yarn orientations and different weave patterns and weave patterns which are not necessarily available from commercial suppliers. So in this loop, where we simulate Meso-scale geometry, simulate macro-scale response, and pass it all into the genetic algorithm, we get improved designs at every pass of the algorithm, and eventually we apply to a converged optimum for our problem, which will be a better design than we started from. So to continue this example, here we work together with Advanced Manufacturing Research Center to optimize performance of automotive floor panel. We wanted to maximize its bending and torsional stiffnesses for the given weight and thickness of the panel. And the constraint on thickness came from the fact that we have already had an RTM tooling and the cavity thickness was already predefined. To demonstrate the benefits of 3D composites, we considered 2 design spaces. One is a layup consisting of conventional non-crimp fabrics used in automotive industry a lot. And the second design space is multi-axial 3D preforms, something like this, where each layer of yarns can have any orientation, not necessarily 0-90. And on top of that, we have a through thickness binder, which can have different weaving patterns. So when we simulate this floor panel using finite element analysis, we will get the map of displacements in bending and in torsion. And if, for example, this panel was made out of aluminum, its performance would be represented by these dots. So certain displacement in bending and torsion. When we consider a composite made out of non-crimped fabrics, we can get different designs. So each of these dots on this graph represent a different layup made out of non-crimped fabric. And we see that some of the designs are actually better in both torsion and bending than aluminum part, which is quite natural. And on top of this improvement in the performance, we of course get the weight saving, just because it's a composite reinforced part, carbon fiber reinforced part. It's already lighter than aluminum. But can we do better? And if we consider optimized multi-axial 3D preforms, we indeed can do better. Again, each of these points represents a unique design of a multi-axial 3D preform. And we see that many of them have much better performance than either non-crimped fabric or aluminum parts. So we can get an extra 5–10% gain in stiffness compared to the optimized non-crimped fabrics, which means that we can further reduce the weight if needed, if we can, for example, change the fiber reflection, or if we can reduce the thickness of the part. So just several concluding remarks. So as in this project, we showed that optimizing the Meso-scale structure of fiber architectures helps to reduce the weight of composite components. And non-conventional architectures provide even more weight saving. What I didn't cover in this presentation is optimization of processing properties, such as permeability. Because you can optimize the mechanical properties, but you can arrive to an architecture which is very difficult to impregnate with resin, or when impregnated, will have a high void content. So what we can do, what we want to do in the future, is to create a multi-objective optimization framework, which we can use to maximize mechanical properties, minimize resin filling time, and minimize the void content. And I think I will stop here, and thank you very much for your attention.
Thank you, Mikhail. Another good presentation from you. The next presenter is George Spackman from the University of Nottingham.
Hi, I'm George. I'm studying optimization of 3D woven T-joints. I'm a final year PhD student at the University of Nottingham. So previous work at the university showed that changing the weaving pattern of 3D woven T-joints can produce different failure properties, and has improved upon the 2D laminates. This is specifically under the tensile pull-off test. So this is done using experimental tests and then followed up using numerical modeling and finite element analysis. So what we want to be able to do is to generate those models automatically to use in an optimization similar to what Mikhail was just talking about. So from the weave pattern, we can produce these flat woven models using TexGen. And we need to determine the order that these wefts interlace in order to be able to fully simulate the models. So if we know the direction of the beating, as shown by these arrows on this model below, and the order of the weft insertion, then we can know the order in which these yarns wrap around each other. And we can produce these models automatically, and we get all the information from the weaving pattern up here in the top left. So the process of model generation is that a Python script using the TextGen functions produces this flat woven model. And so some work still needs to be done to be able to finally produce a good geometry for finite element analysis. So first, nodes are needed to shape the weft yarns around the warp yarns. as you can see here. And again, more nodes are needed at the midsection and moved into place according to the weft ordering information we've gained in the previous from the previous slide. And also the way these yarns nest within each other has been taken from CT data. Then transformations of the nodes are applied and are able to be opened up to transform into the net shape of a T-joint. So here are some example models of T-joint weaves that we've automatically generated using this process. So each of these has 10 wefts and 9 warps and 6 warp stacks. So as you can see, they have varying levels of crossover or not, as the case may be, and varying cases where the yarns stay parallel to each other as they go around the bifurcation area. So the aim is to use these, as I said, in that optimization process that Mikhail was talking about. So they need to be meshed using the voxel mesh. Some tensile pull-off tests will be simulated using Abacus. And so the aim is to be able to find optimal configuration of T-joint weaves for resisting delamination. Yes, I think that's all I've got. Thank you for your time.
Thank you very much, George, for that presentation. So our final presenters today are from the Universities of Manchester, Dr. Vivek Contrary and Dr. Shankator Roy, presenting on manufacturing of optimized preforms.
Hello, everybody. My name is Vivek. This part of the talk is about the 3D preform manufacturing for the car floor panel. I would like to show a video comparing the conventional 3D weaving with the multi-weft weaving system we developed at Manchester. This is a conventional 3D weaving, and as you can see from the video, we are inserting single weft at a time. And one of the problem in this technique is fiber damage. Even though you can see that machine is running really fast, the output is very slow. An elegant way to solve this problem is the patented weaving system. As you can see in the video now, we developed this in this SimCom Hub project. We can put 22 wefts simultaneously in this system, and we further modified this robot to incorporate off-axis fibers. We can make near-net shapes as well, such as T's, Pi's, and I. Sorry, next slide. We developed 2 sets of samples at coupon level to compare the mechanical properties between the conventional 3D fabric and multi-axial 3D fabric. This is sample A. It's a 5-layer 3D structure with fibers in 0 and 90 direction. We use 24K carbon fiber in 0-90 and 6K fiber as the binder. This is a sample B. It's a multi-axial 3D structure with fibers in 0, 90, and plus minus 45. We used a 24K carbon fiber in 0, 90 direction and 6K as binder. Optimization of the structure is still needed depending on the application. This is a table comparing the fabric structures of A without bias fibers and sample B with bias fibers in 45-degree direction. We resin infused the samples. And on the left side is the cross-section image in warp and weft direction of sample A with bias fibers, and on the right side it's sample B with bias. Sample A do not have bias fibers, and sample B with bias fibers on the right side. From the image, you can see that there is almost no crimp in the stuffer layers in sample B. We perform tensile tests in warp direction and in off-axis direction 45 for both sample A and B. Table 1 and 2 on the top is the tensile modulus and strength in warp direction 0 degrees. there is some drop in the tensile modulus and strength in the sample B with off-axis fibers. But if you look at the bottom tables 3 and 4, there is a significant increase in the off-axis tensile strength and modulus. It's nearly 4 times. It's clear from the coupon test we can optimize the performance depending on the application. As Mikhail showed earlier, this is the demonstrator we are working in this project. This is a car floor panel with AMRC. We already made a 1 meter by 1 meter 3D multi-axial fabric. It's me holding the large multi-axial fabrics we developed at Manchester. We can, using the current system, we can make up to 2 meter wide samples. We are looking for partners to develop a commercial 3D multi-axial robotic system. Just to conclude, we already developed a near net weaving capability and reduce the fiber damage. We also know that we can improve the off-axis properties. Mikhail and I are working on infusing the first preform I showed you earlier. We will be doing the testing and further optimizing it for the application. I will pass to my colleague Roy to talk more about braiding and winding.
Thanks, Vivek. Hello, everybody. My name is Shankachur Roy. I'm working at the University of Manchester for optimized cylindrical preform manufacturing. So the objective is to develop novel manufacturing technologies that are capable of producing cylindrical preforms with fiber orientations as desired by the optimization. So the optimized fiber lab will not be constrained by the conventional machine's limitation. In Manchester, we have commercially available equipment. As you can see on the left-hand side, we have a radial braider and then followed by a maple braider. Both of these braiding machines are two-dimensional braiding machines that produces single layer structures, and also a profile braider on the far right-hand side, which produces 3D structures. The 2D braiding machines produce a hollow cylindrical structure. So these are widely used for over-braiding purpose. On the other hand, the 3D braider produces a solid noodle-like structure that you can see on the right-hand side of the slide. Although 3D preform has advantages, as all my colleagues have previously mentioned, 3D profile braiders are not suitable for over-braiding onto a core. So as part of our development to overcome these limitations, in stage 1, we developed a multi-axis filament winding equipment that produces a cross-wound structure, which is earlier mentioned as a quasi 3D structure, you can call it. And the equipment was commercialized by our industrial partners in Signet TexGen. In stage 2, we combined the multi-axial winding method with the capability of adding through thickness reinforcement. As you can see on the right-hand side computer tomography image, the binder is going through the wound preform, and we are further developing this technology at the moment. So alongside the development of, this is the one. Alongside the development of different technologies, we are producing a demonstrator pressure vessel with optimized architecture decided by Mikhail at Nottingham. So for this purpose, we made an inline braiding and winding process that is capable of producing quadriaxial preforms, optimized quadriaxial preform. So otherwise, we call it a braid winding method. You can see an early stage development of this pressure vessel, combining so the preform combines the advantages of both filament winding and braiding technology. So I'll conclude my presentation, and we will show you a video that will showcase some of the highlights of Manchester-Nottingham collaboration. Thank you.
Dry fiber reinforcements are often used to manufacture composite components. Most common, they consist of several layers of 2D fabrics which are simply stacked together. Alternatively, it is possible to use 3D fabrics, which consist of several layers already woven together. They provide near-net shape preforms and offer better mechanical properties because of additional through-thickness reinforcement. We have extended the conventional design space of 3D fabrics, and we were able to show that it is possible to achieve better mechanical properties than is currently possible with conventional 3D fabrics.
In order to overcome the limitations of the current jacquard weaving technologies, the University of Manchester team collaborated with the University of Nottingham team to develop complex robotic fiber placement jacquard weaving and braiding technologies for unconstrained optimization.
For pressurized tubes, braiding can readily incorporate triaxial reinforcement. Combining with the hook reinforcement, we can achieve optimum layups. In Manchester, we developed a complex braid winding machine that significantly expands the process capability to develop quadriaxial layup. This unique machine overcomes the manufacturing challenges of creating optimized fiber architectures.
3D fiber preforming using the patented multi-weft robotic system that we developed in this project is almost like additive manufacturing or 3D printing. Now we can place fibers in any orientation, any thickness along with through thickness binders, mixing various types of fibers such as carbon, glass and ceramics. The platform technology of 3D manufacturing system we developed can be used in composites, technical textiles and in biomedical applications. Currently, we are manufacturing a large car floor panel using the multi-axial preform with through thickness binders. We are looking for potential industrial partners in order to demonstrate this technology in real-life applications such as in electric cars, structural batteries and in space structures.
So thank you to the speakers for the presentations. Please could the speakers now join the stage and we can see if we've got any outstanding questions to answer.
Well, I tried to answer as many questions as I can in the questions panel, but I'll be happy to take any more if anyone wants.
Okay. Well, you're just typing a reply, I think, to Weitan.
No.
Oh, okay, on my screen it says that you're replying. Oh, I don't know where that came from. Okay, so I'll start with a question from Ruben Newell. Says, hi Vivek, I'm interested to know more about how yarn reduced damage was achieved even with an increased amount of weft insertions per shed. Can you give me more information on the typical weaving speeds and warp and binder yarn tensions used?
I mean, typically in a 3D weaving machine, like assemble a donier weaving machine, we put single weft. Let's an example, we got 10 layers. Every weft you need to change the shed. And when you open the shed, for every time you rub the fibers each other and create a lot of fiber damage. In the multi-weft system we developed at Manchester, we simultaneously open 22 sheds. So even though the machine is running really slow, the output is much higher than a conventional machine. And we even tried, we are actually weaving ceramic alumina fibers as well. It's very well in warp and weft directions, even in off-axis. With tensions, it depends on many factors. If it's a 12K, you can work with 70 gram tension on each toe, but it depends mainly on the fiber types. If you're taking 3K or 1K, you need to have much lower tensions.
Okay, thank you, Vivek. And actually, we have another question for you from Weitan. He says, thanks for the great presentation and videos. I wonder what is the mechanism for the 3D preform to keep the shape before the resin infusion? Will it collapse if the Z direction structure is too compact?
Is it for me or?
Yes, sorry. Yeah.
That's right. If you remember in the Prasad's presentation, there is a I shape. We can because of the binder tensions, everything holds in place. It's a really rigid structure. It won't fall off. Normally in weaving, if you see a donier weaving, we cut every weft, but in our case, we have a salvage, which means we lock every weft, so we don't cut the edges. If you cut an edge of a 3D fabric in the middle, the weft or the warp yarn start falling off, but we always lock it in place. That's one of the advantages, because normally, if you if you infuse a sample using a 3D structure, depending on the technician, the fibers will take out the fibers from the edges, and that will change the mechanical properties. In our case, we lock every fibers in place.
Thank you, Vivek, for that answer. We have a question for Mikhail. It says, have you used multivariable control algorithm techniques for the optimization apart from the generic algorithm you presented?
Thanks for the question, Agnostis. No, we haven't used multivariable control algorithm. To be honest, I'm not that familiar with it. I'll have a look at it. We used some other optimization algorithm, or we tried to use some other optimization algorithm. And one of the problems that quite often they either converge to a local optimum or not that suitable for a very nonlinear problems as we have here. Because we have quite a lot of parameters, and say the binder pattern is not a continuous parameter, so it was a bit of a problem. Thank you.
Okay, thank you for that answer. I'm just scrolling down to see if there's any more, because I know you've answered a lot already. Now, Nick, are you replying to Dr. Claudio Barri on his recent question? You're on mute.
Yes, I am. Yeah, Claudio, we don't have any pultrusion activity in the hub at the moment, and maybe we should actually. But as it happens, the University of Nottingham's working on an Innovate UK project with industrial partners on pultrusion. So, I mean, we recognise that as an important element.
Okay, thank you for that. I'm just scrolling through. I think we more or less answered them all. And so do any of the speakers have any last minute comments to make, or anything further to any of the questions they've been asked? Would like to add anything?
Well, there is an interesting question from Chris.
Mm-hmm.
Well, it was to Prasad, but I think all of us actually have something to say about it. Prasad, do you want to start maybe, or do you want to start? So the question is how to actually model 3D woven structures and predict the performance of structures with non-constrained technologies. And I think that's actually the main challenge. If you want to model something, we don't know how it looks like. That's something which requires either a lot of insight. Sorry, I think Prasad disconnected. So it either requires a lot of insight, which means that we need to manufacture something ahead, do a micro CT or a microscopy, and then model it later, or we kind of need to predict the structure using some sort of numerical algorithm. And there are, say, digital chain element methods and other things to model these 3D structures. So that's a challenge.
Yeah. Also, I mean, the weaving system, we advanced quite a lot. Now we can have tapers going up or down in the 3D structure, along with toe steering is possible as well. We even made some demonstrators. So it's all 3D weaving is becoming almost like additive manufacturing now. It's very close to it. So as long as the modeling can predict exactly what we need, manufacturing is catching up with that.
Sorry, my internet dropped off in between.
Yeah.
Would you like to add anything to that question, Prasad? Or?
Sorry, could you repeat the question?
Yes. So the question was, modeling is still an issue for 3D woven structures. How will we overcome and predict performance with non-constrained technologies?
I mean, as Mikhail explained, I mean, as we remove the constraints of manufacturing, it's bringing up all sorts of new unit cell geometries. And it's a matter of TextGen to upgrade and accommodate much more flexible architectures, and also incorporate these new algorithms for optimization, I believe. I think optimization and manufacturing flexibility go hand in hand in progressing this technology.
And Louise and Mikhail are working very hard to do just that.
I think Prasad's connection lost again.
No, I'm here.
I'm here. I'm here. Not
here.
Okay, well, we're out of time now, so let's close the webinar. So thank you to the speakers for your presentations. And thank you to everybody for joining us and for your interest and questions. If you would like to provide any feedback from today's session, then please do so by sending me an email. You can also contact the presenters directly if you'd like to follow up on any questions you asked. You can find contact details on our website, www.simcom.ac.uk. We hope you all enjoyed today's session. Bye for now.
Bye.